welcome back. I recorded this entire video once already, but I didn't turn my microphone on, so this is my second shot at it. This should be a pretty good video. So, what we've done in the past is we've looked at quantitative variables and different graphical displays we can make based on them. So, for example, we've taken our resting pulse rate data. We started with just the data set. We used our calculator to generate a histogram, and then we copied that onto paper and came up with this. So, now that we know how to do that, we want to explain what we can say about it. So, for example, you could be given a histogram like this, or maybe even the raw data, and be asked to describe the distribution. What does that mean? How would you do that? I actually want you to do it. I want you, in your notes, right now, describe the distribution. Whatever you think you need to say about this, say it. Pause the video as you do that. Unpause when you come back. All right. This is what I wrote. Now, if you didn't write exactly that, well, if you did write exactly that, holy cow, me from the past, good job. That's amazing. I'm guessing you don't have this. There might be things that you wrote that aren't here that are useful. There might be things that I have that you don't. But let's dissect this response and see all the different parts that are involved that you need to be able to put in your response when you're asked to describe the distribution. The first thing I want to highlight here is right there. If you said the distribution is, or it is, and you never referred to what the variable is that this is all about, then you've missed a very important piece of your response. In fact, I was an AP grader. I helped grade the AP test this past summer. I graded over 200 responses to the same question. And part of that question asked this. Students wrote everything they needed to write. They had all the pieces that we're about to talk about, except this one. And as a result, even though everything they wrote was correct, they didn't put the context. They didn't name the variable ever. I had to mark them down. Instead of getting it essentially correct, it was only partially correct, which is essentially half the points that they lost for the entire problem because that was missing. The College Board on the AP test really wants to see this. Because if all you say is, it is, then it's almost like you don't know what you're talking about. You need to give this data a name. What is this about? It's not just a bar graph. It's a bar graph, well, it's a histogram, of resting pulse rates of middle school students. And you need to refer to that in your response, because that's what the distribution is about. So, context is first and foremost something you need to write about when you describe the distribution. Make sure you include the context. Name the variable. Okay. Next, you need to include something about the distribution's shape. The shape. Okay, so what are the different types of shapes? I called this right skewed and unimodal. Let's take that one piece at a time. I actually want to start with unimodal. Unimodal, we can break that word apart. Uni, the prefix, means one, right? So there's one mode. Unimodal means there's one mode. There's one bar that's much taller than the rest. One peak to the distribution. One mode or peak. Now, we're going to have lots of practice describing distributions as this course goes on. This is not going to be the only time we talk about it. There might be a histogram that you see that has more than one peak that's about the same. I don't want you to fall into the habit of, oh, there has to be one peak that's higher than the rest. If that's it, even if the next one's really close, then it's not unimodal. Okay, we're looking at the general shape here. It starts high and goes down. For instance, I would not call this a second peak just because it goes down and then up again. The general shape or general trend of this distribution is high to low as you go to the right. So, unimodal is one motor peak. You can have a bimodal distribution. Okay, bi means two. But for something to be bimodal, it's got to be really distinct that it has two peaks. Okay, I'm talking several bars in between the two peaks. If they're at all next to each other, I would consider that unimodal. They've got to be distinct to be bimodal. Okay, you could continue on. If there are 3 modes or peaks, that would be trimodal. 4 would be quad, so on and so forth. In terms of what a statistician would describe a distribution as, unimodal, bimodal, or multimodal. We'll just go straight to multi is many. Many modes or peaks. And you will very rarely ever see a distribution of this shape. They will almost always have 1 or 2 peaks. And that's just because most of the things that we look at, most of the variables that we analyze, only have 1 or 2 peaks, generally. There is, I suppose, a fourth option, and that would be a uniform distribution, and that's where all of the values are relatively similar in height. So maybe something like this. Okay, I'm not saying all the bars are exactly the same height, but there's no real defined peak. They're all about the same. Okay, so it's going to be usually unimodal. There might be some bimodal. Most of the things we're going to look at are unimodal. You might see some uniform once in a while. It's not terribly common either. Okay, but in a graph like this, certainly this is unimodal. In terms of, we also called it right skewed, this distribution here. There are 3 different shapes in terms of skewness or not. There is right skewed, which looks like the one we've got. Okay. The tallest bar is on the left side. There might even be 1 or 2 bars over there. And it decreases gradually as you go to the right. That's right skewed. Left skewed is going to be the exact opposite. You got your tall bars on the right, and then it slowly goes down like that. And again, there could be some variability here. Maybe this one goes back up here, right? But in general, the trend is high on the right, lower on the left for left skewed. Not every distribution is skewed in one way or the other. Some distributions are symmetric. That's where your tallest bars are going to be in the middle. And it goes down either side. Now, this is not art class where symmetry is exact, where like if you cut a paper that's folded and then you open it up, it's perfectly the same on both sides. That's not what we're talking about here. In statistics, close is good enough. It doesn't have to be perfect. As long as it has this general shape, it's considered symmetric. And you'll see as we go later in the course, we have a tendency to use the phrase roughly symmetric for something that has this general shape but isn't perfect. We're big fans of roughly symmetric here. Okay, so in terms of the shape of a distribution, it's usually going to be one of these three. It really can't be much of anything else. And you might also want to comment how many peaks there are. So this one here is unimodal, clearly, and also very clearly right skewed. Okay. Some people have trouble keeping left skewed and right skewed straight. They mix them up. Some people tend to think that, hey, most of the data here is on the left side, so it's skewed left. It's left skewed. But this is right skewed. So, for those of you who took the one semester prop stats course, you might already know this trick to keep left and right skewed straight. To determine the direction of the skew, put a dot above the tallest bar. And toward the longer tail, draw an arrow pointing in the direction of the long tail. Okay. Have that arrow point towards the direction of the long tail. Whatever direction your arrow is pointing, that is the direction of the skew. Okay. Hopefully, if you do this, if you draw that arrow, you won't be confused any longer which direction is which. Okay, I don't want anyone to confuse that on a quiz or a test. I will be very sad. I might cry. And you don't want me to cry over your test. It's not good for either of us. Okay, so context, shape. Pretty straightforward so far. Let's move on. The center of the distribution appears to be between 68 and 88 beats per minute. The center. When you are asked to describe a distribution, where its center is a good thing to talk about. Now, we haven't talked yet about what measure of center we want to use to describe a distribution like this. We're going to get to that later in this video, actually. So for now, the best we can say is something like the center appears to be somewhere in a range. Okay. But once we learn what measure of center we should use, if we have the raw data, which is actually what we did start with here, then we could actually calculate the specific measure of center that we're interested in. For right now, I'm just trying to get you to see that center is something you need to talk about when you're asked to describe a distribution. All right. Context, shape, center, spread. The spread of the distribution is also something nice to write about. Now, again, just like center, we will learn specific measures of spread, quantitative values, actual numbers that quantify spread. We don't know those yet. So, looking at a histogram like this, the best you could do, well, I mean, you could go with the range. You could say all students' heart rates are between 68 and 128. That is true, but it's more useful to say, well, most of them are somewhere in here, which is what we did here. But again, if you have the raw data somehow, if that's what you're given, you can calculate measures of spread and put a nice, neat number on it and say the spread is this. And we'll learn how to do that in a few videos. All right, context, shape, center, spread. We're almost there. Yes, there's a lot to this. Outliers. Okay. If the distribution happens to have any strangely high or low values, make sure you include that in your description. So, this student's pulse rate is set off from the rest. And if you're going to describe a distribution, if that's all it says, then you can look at this visually to determine if there are any outliers. Like, I didn't do any calculations to say that's an outlier. I just said, hey, look, it looks abnormally large. Just like center and spread, we will quantify how to calculate an outlier. So you will be able to do that if you have the raw data. But if all you have is the histogram, it's just by looks. Does it look like an outlier? Okay, then make sure you include that in your description. It's that simple, right? So, these are the basics. Describing a distribution sounds simple. Maybe you had some of this. You probably didn't have all of it. If you did, I'm impressed. Okay? These 5 things you need if you're going to describe a distribution. Let me put that in red so you know it's important. Okay? Describing a distribution needs those 5 things. If you miss any of them, you will not get full credit on a problem that asks you to do such. To get partially correct, I think you need at least 2 of these 4 and context, or 3 of these 4 without context. Anything less than that, you might as well not write anything in the AP's eyes. Okay? You need at least that many to get some kind of credit on that problem. Okay, so it might have been a little frustrating going through this exercise because there were so many things that we couldn't pin down. We don't have measures of center or spread or how to calculate outliers yet. But we're about to get to the point where we can start putting actual numbers onto these things. And we're going to start in just a second with center. You might already know some different measures of center of a distribution. And you might know how to calculate them. So, let's go ahead, get rid of all this, and start with a clean slate. Much better. So, we want to get at the measures of center of a data set. There's more than one. Mean and median are what we're going to talk about here. And you may know exactly how to calculate those things. But we're going to put a more formal statistical context just so you know it exists. First of all, there are 2 ways to calculate a mean. And it depends on whether you're talking about data from a sample or data from a population. If your data is considered to be the entire population, then the population mean is given this notation. This is the Greek letter mu. Okay. So that's a Greek letter, and it signifies a population mean. Right. Now, if we assume that this is data from an entire population, to calculate the mean or the average, well, how do we calculate the mean of a data set? We add all the values up, and then we divide by how many values there are, right? So, in a mathematical definition, that's going to look a little fancier. This is a capital sigma. This signifies a sum, so adding of values. Those of you in pre-calc calculus, you're aware of this. But for those of you who aren't, this just means you're adding up each individual value of the data set. So the subscript I takes on the numbers 1, 2, 3, 4, 5, 6, all the way up to however many numbers there are. Okay, so this is x1, this is x2, x3, x4, all the way up to x9. Okay, So I goes from 1 to, we signify the end of the data set with a capital N for a population. Capital N is the population size. So if the population has 9 values, capital N would be 9. Okay. So we add up all the values, that's what this is saying, and then we divide by however many values there are. Okay. Another way to divide by that is to multiply by 1 over the number of values. So we'll take 1/9 the sum of all these numbers. Okay. You already knew that. That's how I calculate a mean. But in this class, it matters whether we're talking about a population mean or a sample mean. This is the notation for a sample mean. It is called X bar, because it's got a bar over it. How cute. Okay? This is X bar, and it's a sample mean. So, if our data comes from a sample, which virtually every time in this class, we're talking about samples. Okay, samples allow us to do statistics. Population, if we have the data from the entire population, most of this class, doesn't matter. Okay, so this is rarely going to be used, but I wanted to make sure you knew about it anyway. This is what we're usually going to be using. How do we calculate the mean if this is a sample? Well, it's the same basic premise, but there's only one difference. Instead of the population size, capital N, sample has sample size, lowercase n. So that's how far up we count, and that's the number we divide by. I want to be very clear here. The difference between these two formulas is nothing. It all depends on whether this is a population or whether it's just a sample. It's all about the context of the data. These two formulas give you the exact same procedure. It's just a matter of, is it a population or a sample? That's all that matters. So, you probably already knew how to calculate a mean. This is nothing new. So, what is the mean of data set A? Well, we add up all the numbers. Let's assume this is a sample. So I'm going to call this X bar A for the sample mean of A. And we'll just add up all the values. Divide by little n, the number of values, there are 9 of them. And we get 8. So X bar A equals 8. Cool. All right. We should be able to do the same thing for B. Let's also treat it as a sample. So we can calculate X bar B by adding all these up. By the way, data sets A and B, if you haven't noticed, are very similar, except for the last value is wildly different. And we're going to see how that affects these measures of center. 11,976 over 9, and that equals, oh, 1,337. These are just a little different. All right. So that's how to calculate a mean. You already knew that probably. Nothing new here. So let's talk about the median. How to calculate the median. You may already know also how to calculate the median for data sets like these. Maybe you do. But let's go through the process anyway, just to make sure. So we want to calculate the median. I want to make sure I don't screw anything up here. Write what I've got here. Okay. So first step. To calculate the median of a data set, can we read that? Probably. Anything I write up here, I will say at least once. So as long as you can hear me, if the audio's on, we're good. So let's calculate the median of a data set. We're not going to split hairs about whether this is a population median or a sample median. We could, okay? We could do the same thing we did here, but if I'm gonna be honest, the mean gets a lot more play than the median. That being said, it's still important to know how the median is calculated. Okay. So the first thing you want to do order your data set from smallest to largest. Okay. You definitely want to do that first. If you don't make that your first step and you try and calculate the median, you're going to end up somewhere awful. Now we got lucky. Both of our data sets here have already been put in ascending order. If they were all jumbled up and you wanted to calculate the median, you'd have to order them first. Once your data set's in order, how you calculate the median actually depends on n. How many numbers are in your data set. If n is, let's say, odd, okay, so if your data set has 1, 3, 5, 7, 9, or so on values, then the median is the middle value. It's that simple. If n is odd, the median is the middle value. So, I've had students come to me, and for those of you who took the one semester stats course, you already know, I hate this, okay? They're like, oh yeah, I know median. Easy, right? You start at the ends, and you cross off the end values. And then you keep crossing off the values on both ends until you get to the middle. It couldn't be easier. Like a first grader could do that. Okay, yes, I agree. You can find the median that way. However, in my experience, in several years as being a stats teacher, the students who insist on calculating the median by the cross-off method are the ones most likely to get it wrong. I don't know why. My guess is they skip a number or they screw up somehow or something. I don't know how it happens. What I'm saying is, I think there's a better way. You can use the cross-off method, it's fine. But in my experience, there is a better way. Before we get to what that is, I want to talk about when n is even. Because if n is even, there is no middle value. Right? We're always told the median is the value in the middle. But if you've got an even number of values, there is no middle number. In that case, it's the mean of the middle two values. The median is the mean of the middle two values. So, I'm not going to use the cross-off method because you know I hate that, right? So, there is a formula you can use that will help you find the median. It works no matter what. If that is odd, if that is even, you don't have to worry about it because it always works. Here's what it is. The median is always the n plus 1 over 2th ordered value. And that might seem a little strange if you've never seen that before, but it always works. As long as you know n, the number of values you have, you can use this formula to find where the median is. Let me show you. So the median of A is the n plus 1 over 2 value N, for this data set, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So N is 9. So the median is the 5th value. One, two, three, four, 5. So the median of data set A is 9. Now, I will say the main mistake people make when they calculate the median using this formula is they use n plus 1 over 2 and call that the median. When we use this formula, that doesn't say that 5 is the median of this data set. It's telling us where it is. Then you've got to look at your ordered list and see what the 5th value is. Okay, so let's find the median for data set B also. Okay, so again, we want to use n plus 1 over 2. This data set also has 9 values. And the 5th ordered value is 9. Interesting. All right, so both of these data sets had 9 values, and I now realize that was probably a dumb example because you didn't see what happened when n is even. So let's do it when n is even. Let's say n is 12. So we've got a list of 12 values, and we want to find out where the median is using n plus 1 over 2. So you're telling me that if there are 12 values in a data set, 12 numbers, then the 6.5 one, half is the median? What does that even mean? What the heck? If n is even, this formula gives you something 0.5. What the heck? Oh. If n is even, the median is the mean of the middle 2 values. So what this is saying is, for n equals 12 values in a data set, the median is the mean of the 6th and 7th values. So using that formula for the median when n is even, you'll get something 0.5, and you'll need to know that means take the mean of the 2 values this is in between. Okay. So we learned a lot in this video. We learned how to describe a distribution, which is a more intricate process than you probably thought originally. You needed context. You need to describe the distribution shape, center, spread, and outliers. Okay? And then we learned how to calculate the mean and the median of any data set. What we're going to do in the next video, a little sneak peek, let's look at the 2 means and then look at the 2 medians. Interesting. Which one's the better measure of center for these data sets? When should we use the mean to describe the center, and when should we use the median? Guess you'll have to wait until the next video. So until then, have a good day.